Hi, this is Professor Stugard, and today we're going to take a look at an example of calculating flux. So let's say I want to evaluate the flux integral, and again our flux integrals are always our surface integrals, so it's our double integral over our surface of f dot n ds. Now for this particular case, our vector field f is going to be given by negative x in the I hat component, negative y in the j hat component, and z in the k hat component. And our surface S is defined by z equals the square root of x squared plus y squared, which is the surface that defines our cone with a point at the origin and opening upwards. And so we're looking between the planes z equals 0 and z equals 1 for our surface. So again, our surface is that bounded cone. Now, luckily, we want to calculate flux, and this is one of those special cases because our surface z is given as a function of x and y. So we're going to call our function g. All right, so z is going to equal g of x and y, and we use the variable g because we don't want to get confused with f, which already defines our vector field. And then we can apply this formula for flux. Again, in that special case, we can just go ahead and use this formula. So this formula really is our recipe, but before I can start making my recipe and mixing everything together, I'm going to need to gather all of my ingredients. So the first ingredients are going to come from my vector field. So again, I have my vector field f, and p is again my component function in front of I hat, so that's going to be negative x. Q is my component function in front of j hat, so that's negative y. And r is my component function in front of k, which is z. Now, remember, this is a double integral. I'm only allowed two variables. That's it, just the two. And we know that those variables are going to be x and y because it's the special case, which means anytime I see a z, what I'm going to need to do is replace that with what my surface is defined as for that z equals g of x and y. So my r component is going to be that square root of x squared plus y squared because that is, well, how z is defined for this surface. That is going to be my parameterization. The next step, the next thing I need to get together so that I have all of my ingredients for the recipe is going to be to calculate the partials. So I need to take the partials of my function g of x and y now. So you may know how to do this already because, well, I've asked you to do these exact same partials before in this class. Or maybe you've just taken so many square root derivatives that it's just second nature. But for thoroughness' sake, again, if I'm taking this derivative, I'm going to take that square root and write it to the 1/2 power so that I can apply the power rule and the chain rule. And when I do that, well, we bring the 1/2 down in front. We reduce the exponent by 1, which makes it a negative 1/2, which means we're now in my denominator, which means, again, it's the square root in my denominator. And then the chain rule part is that we have to then multiply by the derivative of our inside function. And the derivative of x squared plus y squared with respect to x, well, x squared becomes 2x, and y squared is gone because it's a constant. It's a constant with respect to x. And then we can clean this up a little bit. So the 1/2 and the 2 will definitely cancel out. Like I said, that square root is now my denominator, and that means that the only thing left up top is going to be my numerator, x. So the partial with respect to x is going to be x over the square root of x squared plus y squared. Then we're going to do the same thing to find the partial with respect to y. It's the same process, just change the variable you're taking it with respect to. And so those two partials are going to be the next ingredients that we need for our recipe. And now that we've gathered all of our ingredients, now it's just a matter of plugging everything in. So again, I would suggest that you actually write out the special case, take your time, make sure you replace everything very carefully, especially because, well, I picked this one with lots of signs to be careful of. So it's minus p, so minus, and then again, my p was minus x. Then the partial with respect to x, then minus q, q is minus y, the partial with respect to y, and then plus r. And again, remember, r has got to be in terms of my x and y now. Everything's got to be in terms of x's and y's. We're not allowed to have any z's left over. And so now, well, let's simplify it. Let's actually mix this together and hopefully make it a little bit more manageable before we actually have to do any calculus. So the first thing I see is I have a minus x. So, well, minus minus is definitely going to become a plus. And so then I have x times x, Well, that's going to be x squared, and then over my square root. So that whole thing is going to simplify to x squared over the square root of x squared plus y squared. And then again, the same thing with the y's. Minus minus becomes plus, and then y squared over the square root of x squared plus y squared. And then again, that last radical at the end. Now, I can still simplify this a bit further. The first thing I'm going to do is I see that those first two terms are fractions that have the same denominator, which means I can absolutely add them together and combine them into one fraction. So I get the fraction x squared plus y squared over the square root of x squared plus y squared plus the square root of x squared plus y squared. All right, so we have a lot of x squared plus y squareds going on there. And you might already know where this is headed just because you see the x squared plus y squareds. But again, I can keep simplifying this a little bit further. Now, if I treat that x squared plus y squared as its own quantity, as just that one quantity, then the quantity x squared plus y squared is to the 1 power because it's just itself. And then when I take the square root of it, that's to the 1/2 power. And so I can absolutely use exponents to simplify that first fraction because, well, 1 over 1/2, 1 minus 1/2 is, well, a half. So that just becomes the square root of x squared plus y squared. And I still have that plus the square root of x squared plus y squared at the end. And, oh, that means I have 2 of them. So when I simplify that entire integral, when I plug everything in and simplify it down, I get, well, my double integral over the region D of 2 times the square root of x squared plus y squared dA. Now that everything's simplified, and that's my integral that I need to actually evaluate, I need to know my bounds. And so I need to find my region D, which is going to be the projection of that surface S in my xy plane. Now, I know that that surface is bounded by z equals 0 and z equals 1. And we're bounded by z equals 0 and z equals 1. So when I actually plug those in, well, what's going to happen is that, again, I'm plugging those in for z. So z is really that function, the square root of x squared plus y squared. Well, when I plug in 0, that's just going to be my point at the origin. Because if it equals 0, the only way a square root can equal 0 is that if what's under my square root, that radicand, is 0. And the only way x squared plus y squared is 0 is if both of those quantities are 0. When I look at z equals 1, well, 1 equals the square root of x squared plus y squared. That's going to be my unit circle. Now, you might recognize that already because you can square both sides. 1 squared is 1. And when we square the other side, get sort of our radical, and 1 equals x squared plus y squared is our unit circle. If not, you could always, again, plug it into Desmos and graph it using technology to see what you're actually looking at. And that's what I did right there, and that's the graph I came up with, which is, again, obviously the unit circle. And so the unit circle means, well, let's convert this to polar coordinates. So it is the entire circle, so from 0 to 2 pi, that's how I'm going to bound theta. And then my radius is bounded between 0 and 1. Because again, we're starting at the origin and we're moving all the way out to the rest of our unit circle. So now I also need to convert my integral to polar coordinates. So that means anywhere I see x squared plus y squared, I'm going to be able to replace that with r squared. And my dA is going to be replaced with r dr d theta. So when I make those substitutions, this is going to become the double integral, now, 2 times the square root of r squared times r dr d theta. Now, obviously the square root of r squared is just r, so I can simplify this a little bit further as 2r squared dr d theta. And now it's just, well, taking the antiderivative. So we'll take it with respect to r first. The antiderivative of r squared is 1/3 r cubed. So we have 2 times 1/3, so 2/3 r cubed evaluated from 0 to 1. And again, this is really, really nice when you get to plug in zeros and ones because the zeros are just going to make any polynomial expression go away. And if I plug in 1, that's just the coefficient 2/3. So 2/3 times the integral from 0 to 2 pi d theta, because again I can factor out that constant, well, then it's just my constant function, which means it's multiplied by 2 pi, and so my solution is 4 pi over 3. All right, so hopefully that helped you to calculate this flux integral. And take your time, go through the work, make sure you're actually doing each step with me, make sure everything worked out the way it was supposed to, and good luck studying. Bye.